Dia tak boleh nak gerak-gerak. Okay, mana kelas yang bising? Okay, good afternoon everyone. Okay, just wait for a while for your friends. Okay, we have 4 more students. Okay, 4 students are missing now, so let's see who is not around yet, who is not in the class yet. Ni ada Nurwan ada tak? Wan ada, Tan, Cecilia, Nurul, Nurin, Syamimi, Fahana. Anas ada? Muhammad Anas? Anas ada. Muhammad Haziq, Muhammad Hafiz. Hafiz ada?
Ada doktor, ada.
Ada yang seorang lagi tu lagi. Hafiz ke Haziq? Tak ada.
Haziq kot.
Haziq ada 2 nama tau.
Ya, Haziq ada 2 doktor.
Ni baru 1 je. Okay, Safwat ada Safwat?
Saya doktor.
Imran ada, Muhammad Imran.
Ada doktor.
Siapa yang tak ada ni? Cuba tengok. Ni nama dia orang. Sekejap mana nama orang? Muhammad Anas, Amirul Hazmi ada? Amirul Hazmi? Okay. Satu lagi. 1 more student. 1 more. Who is missing? Farhanani ada? Farhanani ada. Kasya, Pradi, Izzat, Cecilia, Muhammad Haziq, Syamimi, Muhammad Najib, Amir Sufi ada. Nurul Adlina. Nurul Adlina ada. Aiman Iqbal ada?
Ada doktor.
Habis siapa yang tak ada ni? Muhammad Haziq ada? Haziq.
Ada doktor.
Haziq.
Ada.
Buat lagi satu Haziq ada?
Lagi 1
Haziq Izzuddin?
Saya doktor Haziq Izzuddin.
Haziq lagi satu tu?
Lagi 1.
Yang 208-336 tu Haziq apa?
Dia Muhammad Haziq.
Haziq Rafi'i.
Haziq Rafi'i doktor.
Ada tak tu? Haziq? Dia tak ada. Okay. Okay, can I start now? Okay, good afternoon and Assalamualaikum.
Waalaikumsalam doktor.
Okay. Panasnya. Okay, so I just want to ask you about the question I asked you in the lab last time. Okay, the one that you have to design using the Boolean function. That is f a b c is equal to a bar c plus a b bar c plus a b c bar using an 8-to-1 multiplexer and 4-to-1 multiplexer. Okay, So that one, anybody want to show your result? I mean the solution for this question? I think you have submitted, right? In the lab. I gave that question in the lab. Can you check? Implement a t-variable Boolean function. Okay, in the lab, I gave you the question. Have I discussed the answer with you? This one. Look at your WhatsApp. That question. Kakak buat apa kakak? Ni tengok je kat dapur dah. Siapa-siapa masak tinggal. Ada tak? Tengok jap.
Ada doktor, dah submit dah.
Dah submit? Okay. Okay. Can you show your solution here? Okay. If submit, it will take some time for me to check. So let us discuss it now. Because another thing I want to discuss about the test 2. Okay, I plan to have it on Friday afternoon or Saturday afternoon. Which one do you prefer? I know you are free Friday afternoon, right? Next week. Okay? Next week. What is your question just now, Syamimi? Right. From what time? 2 p.m. 2 to 4 p.m. Every Friday. Okay. So meaning you are free from 5, right? Okay. Anybody else free from 5 until at least 7? Okay. Because I need another time that you are free because I know Puan Ruziza's class, their student are not free. Some of the students are not free on Friday afternoon. So on Saturday, because I don't want to take the 2 hours during our class because I already owe you 4 hours. So I want to do the test outside the class hour. So Saturday, what time you are free? Afternoon, from what time? Like 2 or 5? 2 to 4, 5 also can, right? At night also can, right? Okay, let's say like 8 to 10, okay. Saturday, Anybody? Objection?
Is it Saturday 8 to 10, doctor?
Not sure yet. I have to, discuss with Puan Ruziza.
Okay.
Why 8, 10 you cannot? You are not free?
Boleh
Tapi yang ada
je.
koko.
Tapi ada yang kukuh.
Kuku malam?
Malam ke?
Nyak pagi.
Pagi sekejap lagi kot. Awak tak boleh bangun sekarang. Kuku apa pula sekarang ni? Yeah, but Saturday morning you have Coco? What Coco
Ada,
is
Doktor.
that? Because I thought it's not face to face. What kind of Coco you have?
Kuku. Dia sama je Doktor, cuma buat semua online.
Oh, semua online lah. Exercise ke visit-visit pun semua online.
Yes. Dia
Okay.
bagi assignment je.
Okay. Okay, so
At night, I cannot because I have meeting at night.
Saturday night or Friday night?
Both Friday and Saturday.
Betul ke kau pergi dating ni malam-malam ni?
Oh, nak dating dengan siapa doktor? Saya potong single kesian saya.
Anak saya tu kesian dengar. Okay. So night awak tak boleh
Night saya tak boleh doktor.
Friday and Saturday?
Yes.
Oh, seorang je ke?
Saya seorang je.
Okay. Night tak boleh. Okay. Okay, so that's it about the test. Okay, and then, okay, about the solution for the exercise just now. Can you show your solution? At least one student yang berani sikit show your answer. It does not matter whether it's correct or not. We can discuss later. Buat ke tak buat ni? Aminah, are you there? Aminah? Aminah? Aminah tak ada Amirun? Ada tak? Tengok your answer. WhatsApp. Okay. Okay, so look at the answer Wait, let me check. Okay. Can you see the slide? I mean the answer there? Boleh nampak okay, good. Okay. Okay, so let's see the answer whether this is correct. So now you have the table, truth table, and then you take this one as C bar. Is it C bar?
Doktor.
Yeah.
C bar.
C macam mana dapat C bar?
Macam mana
Okay, look at the first answer first. Implement using 8 to 1 8 to 1, so you just copy lah. Okay, according to the F. So let's see you label as D So D naught is 0, connected to 0. 1 is connected, D1 is connected to 1. D2 connected to 0. D3 connected to 1. D4 connected to 0. D5 connected to 1. D5 6 to 1, 7 to 0. Okay, so that is correct. So you have select them A, B, C. Okay, that is correct. Okay, so now look at the one with 4 to 1 marks. Okay, so you select is, for example, here your select is BC. BC, so you have D naught, if you use this table, the one that is not the truth table, okay, the other table, like this one, this part I like. Okay, this much easier. So you have 0, 1, A and A bar. So D naught is connected to 0. Okay, D1 is connected to 1, D2 is connected to A, and D3 is connected to A bar. So that is correct. Okay, using that diagram. Okay, so this one I have to check because I cannot see your answer here. You said it's now C bar. Okay, this is C bar. Is it C bar, that one? Okay, should be okay, this one. Okay, any question that you want to ask before we proceed? No question, Okay, so before that, since your topic to be covered in the test start with adder until marks. I don't think counter will be in the topic because the other class they have not started with the topic of with the counter yet. Okay, let me see. Okay. Okay. So before that, I want you to look at this YouTube. This is on parallel adder.
Welcome to this presentation. Let's revise what we have learned till now. We have added two single bit numbers. Let's say A is the first number, that is equal to 1, and B is the second number, which is also equal to 1. These are the two single bit numbers, and we have added them with or without carry. So if I add them without carry, and let's say the carry input is also 1, so we will not consider this input carry because we are adding these two numbers by using the half adder. So the result would be 1, 0. What we get when we add these two numbers by using the half adder, and when we use the full adder, we will consider this carry, and the sum will look something like this: 1, 0, and then again we will add the carry input. This one is carry input, and we will have 1 of 1 as the final sum by using the full adder, and this is what we get by using the half adder. So this is all that we have learned till now. We have only added the single bit number. We have not added the multi-bit number like 1011, 0011. We have not added the two multi-bit numbers, and that we are going to do in this presentation. We are going to obtain 4-bit parallel adder by using full adders. So we will add two numbers A and B. Both A and B are having 4 bits. As you can see, A is equal to A3, A2, A1, A0. These are the 4 bits. A3 is MSB, A0 is LSB, and B is also a 4-bit number. So we are going to add this 4-bit number by using full adder. So let's see how to do this. As we are considering the full adders, we can definitely take carry from the previous sum. A0, B0 are the 2 bits that we are going to add, and we will consider the carry in from the previous sum. And as you can clearly see, this is the first sum that we are going to do. The first 2 bits we are going to add. So definitely Cn is equal to 0 for this first full adder. And after the addition, let's say S0 is the sum and C0 is the carry output. Now one very important thing that you must keep in your mind. When you add 5 with 5, these are 2 single digit numbers, but the sum is 1, 0. This is 2 digit. This is single digit, this is single digit, but the sum is 2 digit number. In the same way, when you add 2 4-bit numbers, then sum may be equal to 4-bit or it may be 5-bit. So in this case also, when you add A, B, the sum may be equal to 4 bit or it may be equal to 5 bit. Again, we have to use another full adder to add these 2 bits, A1, B1, and we have to consider this C0, the carry output from the previous sum, and this will act as the carry input. This will act as the carry input for the addition of these 2 bits. And let's say we got S1 as the sum and C1 as the carry output. Again, we have to follow the same procedure. This C1 will act as the carry input for A2, B2, and S2 is the sum, C2 is the carry. Again, we have to use C2 as C in carry input for A3, B3, and S3 is the sum, and C3. Now C3 is what we got after the addition of the 4th bit, and this C3 will again act as the carry input for the next sum, and we have 0 to add 0 plus 0 plus C in, and C in is C3, so we will have C3. So this is what we got as sum, and it is C3, S3, S2, S1, S0. So in total we have 5 bits as our sum, and depending upon the values of A0, A1, A2, A3, B0, B1, B2, B3, C3 can be 1 or it can be 0. If it is 0, we have 4-bit sum. If it is 1, we have 5-bit sum. Now how to implement this? We will implement this by using full adder. Let's consider the addition of first 2 bits, A0, B0, B0, A0 will act as the 2 bits, and we will consider the carry input from the previous sum, but it is equal to 0. S0 is the sum for the first addition, the addition of the first 2 bits, and this is the carry output C0, right? It will act as the input carry to the next full adder that we are going to use. This is the full adder, and by using this full adder, we will add B1, A1, S1 is the sum, and again we will have the carry output. Carry output is C1, and it will act as input carry for the next full adder, and the next full adder use to add B2, A2, sum is S2, output carry is C2. Again, it will act as the input carry for the next full adder, and the last full adder we will use to add B3, A3, and the sum is S3. Very simple. And the output carry for the last full adder, is C3, and by including C3 along with the sum that we have obtained from the different full adders, we will get the final sum. So this is how you can have a 4-bit parallel adder by using 4 full adders. Now we can add multiple bits also. This comes in an IC package, and the IC is 74HC283. 74HC283 is the IC for 4-bit full adder. You can purchase this from the market. We also have the IC for 8-bit full adder, but I think we don't have the IC for 16-bit full adder. You can definitely obtain 8-bit full adder by using 4-bit full adder. If you have this IC, you can cascade it like this, and you will have 8-bit full adder. This is very popular circuit, and sometimes it is shown in book like this. B0, 1, B2, B3. For B, we have A0, A1, A2, A3. The second number that we want to add, S0 is the first bit of sum, S1 is the second bit, S2 is the third bit, S3 is the fourth bit, and we have C3, that is the carry output for this 4-bit full adder, and we also have the carry input. So this is how 4-bit full adder can be represented, and you can also have the 8-bit full adder by using this 4-bit full adder. Let's see how to do that. We will need 2 4-bit full adders. So let's make 2 4-bit full adders. These are the 4-bit full adders. 4-bit full adder. Right? And we want to add 8-bit numbers. Let's say A is the first number and it is having the bits A7 all the way to A0. B is the second number having the bit B7 all the way to B0, and we will obtain the sum. And sum is S7 all the way to S0, including the carry output, and in this case carry output will be 7. So this is our sum, and you can easily implement it by using 2 4-bit full adders. This is B 0 to 3. This is A 0 to 3. We will have sum. 0 to 3 carry input. 3. Here we will have sum 4 to 7, and we will obtain this sum 4 to 7 when we add the bits B 4 to 7 and A 4 to 7, right? And finally we will have C7. So by using 2 4-bit full adders, we can have this is 8-bit full adder. So this is all for this presentation. If you have doubt regarding any part of this lecture, you may ask in the comment section.
Okay, so you understand if you are given you are given like
Hi there, I'm Claudia.
if you are given like 4-bit IC but you want to design higher bit, so you can cascade it. Okay, so you have to know that, eh? Okay, so now let us continue with the lecture notes, eh? So today, yes. Macam mana? Oh yeah, yes. Marks, decoder, coder, marks, demarks, decoder, encoder, adder, subtractor, latch, flip-flop. I think the counter is not included yet. Okay, because the other class, they haven't touched about counter yet. Okay, so make sure you know this just now adder, and then you can find out what how to design subtractor. I think you know already because we have done that in your lab, right? Subtractor, remember? So make sure those are related, whatever you have done in lab. Sure, that is to give you more understanding what you have learned in theory. So you should know. Okay, so today we continue with a shift register, a new topic. If we finish early, we finish everything earlier than week 14, then after that you can free to study on your own, yeah. And then one more thing, it's about your test one. I already got the marks. I will let you know. Okay, later. They are good. There are some students did very well, and some students did not get, good result. Why? The problem is why you did not answer the question. You just leave it blank. You did not try to answer it. No attempt. You just leave it blank. So at least you must try to answer all questions. Is it because you spend more time searching for the answer in internet? I don't know. You should study before the test. Don't rely, okay, I can Google. It's not easy to Google. Okay? Dengar tak saya cakap ni? Saya tahu siapa-siapa yang ni. I know the names already. Who did not do very well. Okay? So make sure test 2 you try to get good result, because otherwise your grade will be much lower. Okay, and then for the lab, after you have finished all the report and simulation, then I want you to do presentation. You can record it and then you post to me, or you can link in the Google Meet so I can check, and then we can have a session for question and answer later on. Okay, that's it for the lab. Okay, now shift registers. Okay, so basic shift register operation. Okay, you see the arrangement here. A shift register is an arrangement of flip-flop. Okay, this refer to flip-flop, all these boxes here, with important applications in storage and movement of data. So some basic data movements are illustrated here. So there are a few examples here. The first one is serial in, okay, shift right, and then serial out. You see here, serial in, shift right, and serial out. Okay, second one is serial in, okay, serial in, shift left, and then serial out. And then you have another one, parallel in, serial out. This is parallel in from the top here, and then serial out. Okay. The next one is serial in, parallel out. And then this one here is parallel in, parallel out. And then you have rotate right. See here, it's rotate to the right here. And then here is rotate left. Okay. Okay. Okay, serial versus parallel register. So serial in or serial load, register takes the data into the first flip-flop one bit at a time. So the flip-flop cannot be loaded in parallel. Serial out, register provided output only in serial mode out of the last flip-flop. So the output of the other flip-flop are internal to the circuit, not connected to the output terminals. And then you have here parallel in or parallel load here. Register allows loading all bits at the same time. Okay, all at the same time. And then parallel out register allows reading all shifted bits at the same time. Okay, so this is the difference between serial and parallel register. So now look at here, serial in, serial out. Okay, shift registers are available in IC form or can be constructed from discrete flip-flop. Okay, as shown here, this is from the discrete flip-flop with a 5-bit serial in, serial out register. Okay, so look at here. This is 5 bit. 5 bit meaning you have 5 flip-flop. 1, 2, 3, 4, 5. 5 flip-flops. So it starts from FF0 or FF0, FF1, FF2, FF3 and FF4. 5 bits, 5 flip-flops. So this is serial in. You look at the input here. Okay, the input start with 1 here. This part here is serial data output. And then this clock here, you see, the clock is connected to all flip-flop. So this is synchronous or asynchronous register.
Synchronous.
Okay, this is synchronous, yeah. And then there is no bubble at the clock here. So all refer to the positive age, yeah. Okay, now each clock pulse will move an input bit to the next flip-flop. For example, 1 is shown here as it moves across. So look at the diagram here. Okay, you can see here 1 clock and then move to the output, and then from flip-flop 0, okay, another clock goes to output of FF1 and so on and so on, and goes to the serial data output. Okay, so serial in, serial out shift register 5 bit, the same as you have seen just now. But now you can see the timing diagram. Okay, so the same diagram just now. Okay, so there is no bubble here. So this refer to positive age. So look at the clock, positive age. Okay, so this is the data input. Okay, data input you see here. You have here 1, 1, 0, 1, 0. So what happened at Q0? You see here, Q0 positive age. So you have positive until the next clock here, still positive here. Okay, it goes here. This is D flip-flop. Remember D flip-flop, Q is equal to D, right? Okay, Q follows D. So here is high, so it becomes high until the next clock here. Now this is low, okay, low until the next clock here. This is high, so you have high, and then here this point is low. Okay, that is for Q0. Okay, and then this Q0, okay, this Q0 goes into the next flip-flop. So it becomes data for F1. So look at what is Q1. Okay. So now at Q1. First clock here, positive here. Okay, now this is negative. Negative, so it goes low. And here is this clock. Q0 is high, so you have high. Until this clock here, this is still high, so it's high. Okay. This clock here, this is low, so you have low. And this clock here is high, so you have high. Okay. And then this Q1 become input for flip-flop number 2. So now look at this clock. Okay, and Q1. Q1 is low here, okay, until this clock here, this is high, so you have high. Okay, at this clock, still high, so high. At this clock, this is low, so low. Okay, now Q3 becomes the input for flip-flop number 3, where you have here, sorry, Q2, Q2 goes in here, so Q3. So now look at here, Q2 becomes the input. So this clock is low, okay. This clock also low, still low. This clock Okay, so low, so you have low here. At this clock you have high, so you have high. This clock here is high, so you have high. And then look at the last one, Q4 here. Q4, Q3 is the input. So at this clock, low. At this clock, low. This clock, low. This clock also low. This clock is high, so you have high. Okay, so data bits stored after 5 clock pulses. Okay, so look at the data just now. You have 1 1 0 1 0. So this is your data will be 1 1 0 1 0. So see here the data bits stored after the clock passes. The last clock, that only you can get the output. Okay, after the 5th clock, because you have 5 here. Do you have any question?
Tak ada.
Ada So easy to understand because this is serial in, serial out. So meaning you have some delay, right? Because you must wait until the 5th clock. That is for serial. Okay, so this is a basic 4-bit shift register. Can be constructed using 4D flip-flop. As shown here, the register is first cleared, then forcing all 4 output to 0. So the input data is then applied sequentially to the D input of the first flip-flop on the left, that FF0. So during each clock pulse, 1 bit is transmitted from left to the right. So assume a data word to be 1001. So the least significant bit of the data has to be shifted through the register from FF0 to FF3. Okay, so this is for 4 bits. Okay, now you look at this. Okay, first it will be clear. Okay, 0 here. And then 1001 goes inside the flip-flop. Okay, you see? Can you see the movement? Okay. You see the movement there? Then only it's stored in there, the flip-flop, and then it goes out. Okay. Okay, an application of shift register is conversion of serial data to parallel. Okay, serial to parallel form, For example, assume the binary number 1011 is loaded sequentially, 1 bit at each clock pulse. Okay, look at this serial data input. Okay, 1 clock it goes to the output there. Okay, then it goes to the input, the output of the next flip-flop, and so on, and so on. Okay, so 1011. 1 go first, and then the 0 goes in, and then 1 goes in, and 1 goes in. Okay, so you get the output here taken here. Okay, so FF3 is the most significant bit. So you take the value 1011. After 4 clock pulses, the data is available at the parallel output. So this is the parallel output, Okay, so now look at this diagram of serial in, parallel out, shift register. Previous slide, this one. Okay, this is 4 bits. Okay, 4 bits, you have 4 flip-flop. The X, so stop already because the input is only for 4. Okay. Okay, so that's it. So this is the same 4-bit serial in, parallel out. Okay, so parallel in goes in here. This using the D flip-flop, and here is the symbol. Okay, data in. For data in, D flip-flop, and then you have clock there, and then this is the parallel output. So now look at the data in. You have 0, 1, 1, 0, and this is the clock. So you look at here, there is no bubble. So you look at the positive edge. Okay. So you see here at positive edge. Okay, so you have there low here. Okay, until the next clock, then you have high. Here also high, and then here is low. You can start here with low, but here it start with high. So you can start also with low, because this is undetermined. You do not know. You have to clear it first. If you want to design, right, you have to clear whatever inside the register. So here you see here, this is 0. Okay, so you look at the next flip-flop, F1. F1, then the output of Q2 become the input for flip-flop here. Okay, so you find what is Q1 here. So at this clock, okay, because this is high, so you have high here. And then here is low, it becomes low. Here is high, high, and here is also high, so high. Okay, now the next one, this Q1 become the input. So at this clock, this is high. Here also high, here also high. Okay, and then at this clock, this is low, and then this clock is high. For Q3, Q2 become the input. So this is high, high, high. Okay. At this clock also high. This clock, this is low, so low. Okay. So this is a parallel output. So you take the output at this point. That is 1, 0, 0, 1, 1, 0. Okay. Any question? Kering dah tekak saya.
Tak ada.
So this is serial in, parallel out, shift register. So data bits are entered serially and the data bits are taken out at the register. Okay. So once the data are stored, each bit appears on its respective output line and all bits are available simultaneously. Okay. So a construction of a 4-bit serial in, parallel out register is shown below. You can see this is the diagram here. So in the animation below, the 4-bit binary number 1001 is shifted, okay, to the Q output of the register. Okay, first this is 4-bit, yeah. That's why you have 4 flip-flop here. Now look at the bottom here, the animation here. So first it must clear the register. Okay, and then serial in goes and then the output is taken. Okay, it should stop there. Okay, for example here, it should stop there. So clear and then the data goes in and then you take the output. Okay, any question? Okay. Okay, this is 74HC164A shift register. Okay, it's a CMOS 8-bit serial in, parallel out. Shift register and then VCC can be from 2 to 6 volt. Okay, and then you have here, okay, active low, clear here. You have clock, you have serial input A and B, okay, and then you take the output here. This is parallel output, yeah. So one of the two serial data inputs, okay, here A or B here, may be used as an active high enable to get the other input. So if no enable is needed, the other serial input can be connected to VCC. Okay, so the 74HC164A has an active low, asynchronous clear. Okay, data is entered on the leading edge of the clock. Okay, so look at the diagram here. Okay, and then you have, okay, look at the waveform. Okay. Waveform for the 74HC164A are shown here. So notice the BX. Okay, this is the B. X as an high input. Okay, it's always high input. Enable for the data on A as discussed. So this is the B is high. So the output will perform when B is high. Okay, so before, if B is low, disable. Okay, so this is the input data actually. This is, okay, you have here low, low, high, high, low, and so on. Okay. Okay, so this part is clear because this is active low clear. So it start with clear. Okay, and until here, nothing happen, right? Okay, and then it will, okay, the data will go in at this part. Okay, when B is high. So that's why you have here high, low, high, high, the same as what you have in A here. So shift register is shift, meaning it shift. So the data will be shift every for every queue here. You look at here the data, okay, it will shifted. So the data output is taken parallel. So you will take the data here. Okay, so it will be 1, 1, 0, 1, 0, 0, 0, 0. Okay, at this point it will be clear because this is active low. Okay, so as with CMOS device, unused inputs should always be connected to a logic level. Unused output should be left open. So this is mentioned here. If you go to the lab, what you have to do with the unused input and output, yeah. So meaning the input always connected to a logic level and the output will be left open, yeah. Okay, so I think we stop there. So we continue next Monday. Okay. Okay.
Doctor, I ask a question.
Ah.
Doctor just now said that this is the parallel shift, right? So the output will take at the second clear. Then the output we get, actually how we know that is the output?
Oh, until the end clock. Because this you have how many? You have how many bits? You have 7, right? 8, sorry. 8. You have 8, right? So after the 8 clock, before it goes to the final clock. Okay, the 8 clock is where you take the output.
Okay, but then how we know the output is same as what we had goes in the input?
Oh, it's supposed to get the same.
Means the AB, right?
Ah.
The AB is have an.
No. The B is used as enable.
Okay,
But
so
A is the input.
the input.
Ah.
So the 110, the output of Q7 is the most significant bit.
Yes. Okay.
Okay.
Okay. Okay. Any more question? Okay, no, we meet you. I meet you next week, yeah? So the test also next week on Saturday or Friday. Let me discuss with Puan Rosriza. Okay? And I will put up your marks in Putra Blast. Okay, bye.
Thank you, Doctor. Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Baru ada suara.
Thank you, Doctor.
Thank you, Doctor.
Amina ada Amina.
Thank you, Doctor.
Okay. Okay, see you. Bye-bye.